Hey, my name is Caleb Walker. I'm a mechanical engineering student at WSU.
Hi, this is Janokshan. I am a mechanical engineering student, final year, and I'm doing senior capstone design for this semester. And I'm part of this team to do the estimate of leakage losses in a 3D printed miniature internal combustion engine.
Hi, my name is Matthew Lucas. I am a mechanical engineer.
Hello, this is Don Isametsa. It's for Senior Capstone Design, leakage test for mini 3D printed internal combustion engine.
This project is designed to provide 3D printing tolerances for Aerojet Rocketdyne. To accomplish this, leak tests will be conducted analyzing the leakage through the piston cylinder gap of their miniature 3D printed internal combustion engine. The top image is a photo of the internal combustion engine. This engine is 3D printed from a proprietary aluminum alloy. Aerojet Rocketdyne has been developing advanced energetic and propulsion systems for decades for the U.S. Department of Defense, NASA, and other organizations. Aerojet Rocketdyne is investigating many 3D printed four-stroke internal combustion engines for use by NASA. We were set to leak test the piston cylinder gap of a single cylinder. The middle image shows all the design measurements given to us in the 3D CAD file. This project is designed to provide 3D printing tolerances for Aerojet Rocketdyne. To accomplish this, leak tests will be conducted analyzing the leakage through the piston cylinder gap of their miniature 3D printed internal combustion engine. The bottom image shows the 3D printed image before the part was machined to its size. You can view all the special support structure that stabilized the part as it was printed.
Simulation. 9 COMSOL models were made containing 1, 10, and 100 micron gap values with input velocities of 0.1, 1, and 10 meters per second. This is going to tell us the type of flows we will see in the experiment. Below are the COMSOL velocity results and a graph of the COMSOL results for a 1,000 micron gap. Verification. Using the equation for annular flow, we were verifying the COMSOL results mathematically. We solve for delta P in the annular flow equation, and below is our results.
A SolidWorks model was obtained and using the dimensions converted to CATIA. The model was modified to accommodate testing by removing the fins, elongating the cylinder head, adding pads for mounting and pressure sensors, and designed a cap. These models were 3D printed using PLA plastic. On the left is the SolidWorks 3D model, the middle is the 3D CATIA model, and on the right is the 3D printed plastic model. Here is a schematic diagram of the test setup. On the right, an air compressor sends compressed air into a solenoid valve that then passes through into a flow meter and finally enters on one side of the piston. Pressure sensors on the bottom each measure a pressure on one side of the piston and then send the signal to the computer. A LabVIEW program was designed to collect and analyze the pressure differential and airflow. On the left is the LabVIEW front panel. Two graphs are shown. One shows the two pressures, one before and one after the piston, and the other graph shows the differential pressure between the two. On the right is the block diagram. In this block diagram, it contains a DAQ assistant that passes all its signals into the two graphs. All of these are inside a while loop.
So we took 3 different piston sample and same measurement of cylinder for this experiment. Which one is 26.25 millimeter, and the second one is 26.5 millimeter, and the third one is 26.75 millimeter piston sizes. And then after we conducting the experiment, we got the results as you can see in our poster. We tested two 2 times for each piston sizes, but the results looks like same, and there were not much difference changing in there. But the third piston's tolerance did not give us a chance to get results for more flow. And the last reading for the third piston is high flow, is on a high flow. And on your left you can see our experiment structure for our experiment, and on your right you can see 2 graphs. The first graph is for 26.25 millimeter piston, and the second graph is for 26.5 millimeter for the piston. That the second graph is a little higher than the first one because of the pressure. And thank you. If you have any question, please let us know.